All right, how's it going, everybody? We are here on Sunday, April 11th, and today we're going to wrap up section 11.1. This is sort of our second 11.1 video here. And basically, before we wrap up 11.1, the thing we got to talk about is proof by induction here. It's one technique for proving that statements are true in relation to positive integers. The reason that we need this is because we need to be able to prove that sequences have certain features. Sequences are always defined based on integer indexes, and so proof by induction is very typically well suited for discussing things surrounding sequences here. Recall from the previous video that when this came up in conversation, it was surrounding the monotonic bounded theorem. So this is what we wrapped up the previous video with. The monotonic bounded theorem is going to say that every bounded monotonic sequence is convergent. Our goal is to show that a sequence is convergent. So the monotonic bounded theorem says one way we could show that is to show that the sequence is both bounded and monotonic. Those are two separate ideas, that it has an upper bound and lower bound, and that it is always increasing or always decreasing in value with every additional index that when we increase n by 1, we always are guaranteed to get a larger number every time or a smaller number every time. Right? So what this really says is to apply this theorem, to take advantage of this theorem, what you need to be able to do is you need to be able to prove a sequence is bounded. You need to be able to prove a sequence is monotonic. If you can prove both of these things, then you can just simply state, by the monotonic bounded theorem, it's convergent because I proved it's bounded and monotonic. Each of these things are things that are potentially able to be done with proofs by induction. So that's why we're going to go ahead and look at that topic here today. So what we're going to do is we're going to look at what is a proof by induction. We're going to do a very generic first example. I think it's most people's first example with the proof by induction. Then we'll come back and revisit a monotonic bounded statement where I'm going to say, here's a sequence, prove it converges. We're going to prove that that sequence is bounded. We're going to prove that it's monotonic. We're going to conclude that it converges by this theorem here, and that'll be the wrap up here. So, proof by induction. In general, proofs by induction are used to prove that a mathematical statement is true for the positive integers, or at least a subset of the positive integers. We're going to start with a very simple base case example right here. We're going to prove that the sum of the integers I, if you're going to add up the first I integers, right, starting with I being equal to 1, going up to I being equal n, we're going to use, right, there's a summation, we're going to add up all of those numbers, all of those integers, and the claim is that the formula is going to be dependent only on what the upper bound number is, n, right? So this is saying, this is me like asking you, hey, what's the sum of the first 100 positive integers? The claim is that the answer is going to be 100 times 101 divided by 2. That's the claim that we're making. What we want to do is we want to prove that this is, in general, a true statement right here. And what we should do is we should first look to see if we even believe this, right? So I might make for myself a little bit of a table right here, and I want to say to myself, what's n? What is the sum from I equals 1 to n of I going to look like? And what is the formula n times n plus 1 over 2 going to look like? So let's go ahead and just kind of investigate this. This is just us doing our little bit of numerical exploration right here. This is gathering evidence. You certainly could never prove that this is true by doing a little bit of computation because you'd have to do an infinite number of checks. But we think that we can kind of at least get grounded with this thing right here. So one thing I'm noticing here is that since I is going to start out at the lowest value of 1, the lowest value it makes sense for n to be is also 1. So if n is 1, then the sum of the first 1 numbers is just 1. And that's going to, and I'm going to say it's equal to 1 just for our consistency for the rest of the column here. And our second thing, the other side of the equal sign, we're seeing 1 times 1 plus 1 over 2. And that's certainly equal to 2 over 2, which is certainly equal to 1. So that was the obvious case right there. Now if n is 2, then the sum of the first two integers is 1 plus 2, which is going to give me 3. For our formula over here, the upper bound is 2, so I'm going to get a 2 times 2 plus 1 over 2. 2 and 2 are going to cancel here, leaving us very clearly with 3. If we check it out for 3, 1 plus 2 plus 3 is going to give me 6. 3 times 3 plus 1 over 2. This is 3 times 4, which is 12. 12 over 2 is going to be 6. So it seems like these are matching up. 136, 136 right there. This is my evidence collection. This is me saying, okay, I at least believe I believe it. Unfortunately, belief has sort of no place in science whatsoever. We like proof. And so we're going to pursue proof that this is actually a legitimate formula right here. I could probably come up with about 1 billion different formulas that would agree on the first three terms and then disagree afterward. So this is evidence, but this is not proof. So what are we going to do for our proof by induction? So here's the deal. Every proof by induction, I might as well, let me just get this on a fresh page right here. Every proof by induction has two steps. You're always going to make two general statements with every proof by induction. You're always going to prove that it is true for some base case, some simplest case example. It's very, very typical for your base case to be n equals 1. But then again, that's only true if the initial statement is true, is being claimed to be true for integers as small as 1. I'd say that's the most common thing, 1 or 0. But it's totally the case that sometimes we say, hey, this equation is going to hold for all integers above 7. Then n equals 7 would be the base case that you'd be wanting to be verifying. And that's uncommon, but not wildly uncommon. That's the easy step right there. The induction step, or the inductive step, is to say, show that if the statement were true for the n case, if it's true for the n case, this is the n case right here, then it must be true for the n plus 1 case. So what we're going to do with the inductive step is we're going to say, assume that this equation is true for using n as the value of n. Then what we want to prove is that it is true if n plus 1 is in fact the value of n. This is saying, given that it's true for some case, prove that it's also going to hold true for the next case. And let's think about why this is going to work. What we want to do is we want to prove that that statement, that equation up there is true for possibly an infinite number of possible values. And in fact, most cases, this is true for all infinite number of positive integers that there are out there. We obviously can't do this exhaustively by checking every single one. Otherwise, you'd have to do literally an infinite number of computations to prove that we're going to get the same value on the left and right side of the equal sign. Instead, this two-step process for proof by induction is going to logically progress us through this following idea to verify that by doing only those two steps, we're going to verify that it must be true for an infinite number of possible cases. So here's why this works. And I need to scroll up here, I guess. So I'm reading these two steps, and those are what I'm referencing down here. Oh, how did that get underlined? Based on step 1, the base case step, the statement is true for the base case n equals 1. We're literally just going to plug in n equals 1 into the formula and show that it's correct. Our start to a proof by induction is going to be to show that we're going to get 1 from this and 1 from this. And so the statement holds for the case where n is equal to 1. Now, based on step 2 for the induction step, and the fact that it's true for the case n equals 1. So remember, this inductive step is going to say, show that if it's true for the n case, it must be true for the n plus 1 case. Well, what is the n case going to be for us to sort of start out right here? Well, we've already verified that the n equals 1 case is true. So what we're really doing with this inductive step is we're saying, listen, I know that it's true for n equals 1. I'm going to then say, now that I know it's true for n equals 1, I want to use that piece of information to prove that it's true for when n is 2, right? The next n size. Then I now have proven that it's true for n equals 2. So now, based on step 2 and the fact that the statement is true for n equals 2, it therefore must be true for n equals 3, right? So when we show this generic, if it's true for n, then it's true for n plus 1, if we start that at the seed case of n equals 1, then n equals 1 is going to show that it's also true for 2, 2 shows it's also true for 3, 3 shows it's also true for 4, because we did it in general by showing if it's true for any one case, it's true for the next case. That's what the inductive step is showing. This is going to then logically prove to us that this must be true for every single integer value of n by only showing it's true for a base case, and by showing if it's true for any one case, it is true for the very next case. And every time I say case here, I mean integer value of n, right? And before we go and do the example, I want to point out that this inductive step can change a little bit. Here I'm claiming that I want to verify that it's true when we use n in the n slot, and then use that to prove that it must be true if we use n plus 1 in the n slot, showing it's true for the next largest integer that we use in our sequence formulation. However, sometimes we modify this ever so slightly. You should think of this more generically as the inductive step is saying if it's true for a case, we typically start with the case n, but it can be other things, then it's true for the next case, right? So sometimes we'll do things like assume it's true for the n minus 1 case, and then therefore show that it's true for the n case. Allow the n minus 1 case to prove the n case for us. That's still showing us this progression, showing that if you know one case, you then therefore know the next case is also true. Other times, we might do something even crazier, like assume that the n plus 5 case is true, show that the n plus 6 case is true. Sometimes doing things like that will help really smooth out the algebra that you're going to have to do along the way to show this verification. So even though that seems a little bit wonky right here, there you just might end up in algebra land. What would really help you to have an n plus 5 instead of just an n and make all the algebra simpler, then this is a completely acceptable route to go. You might need to make some other technical statements to cover those previous 5 cases that you skipped out there in general, but like that's not, or to say maybe your base case needed to start at 5 or 6 or something like that, but those are just some technicalities. The broad strokes of it here is that the inductive step 2 of every proof by induction is always show that if the statement is true for one case, it is true for the next integer up's case as well. So let's go ahead and see this in action for our simple example, and then we'll return to our bounded monotonic sequence example. So we're going to go ahead and we're going to prove this statement here, and we're just going to follow the 2 steps of every induction proof by induction. And man, I literally, when I write my proofs by induction, I write like 1 parentheses, base case, underlined, colon, and I show the base case is true. When I'm done with that math, which is almost always really easy, I then say 2 parentheses, inductive step, and I say assume it's true for the n case, and I write out what the n case is, and then I say I want to show the n plus 1 case, and I go ahead and I do the algebra that's going to show that here. So let's go ahead and prove that this is overall a good formula for the sum of the first n integers, that you're going to get n times n plus 1 over 2. So verifying the base case is almost always super duper easy. All right, our base case here is, I'm seeing here that, let me highlight this right here, I equals 1. This is our base case. Base case meaning, what's the smallest value of n that you think this formula is going to be true for? Well, I think n equals 1 should technically make sense the way I've formulated this. I don't see any reason why I shouldn't be including the sum of the first 1 integers. Like, that's not that great. That's kind of stupid, but it makes sense, right? The base case here, I know that I'm saying I equals 1. We're referencing what the variable is as using the letter I. But if I were to say my upper bound n is going to be 1, then that means we're doing our sum from 1 to 1, basically just using 1 as our only indexer I right there. So to verify the base case, all I have to do here is say this sum from I equals 1 to 1 of I is equal to 1, because it's literally, there's nothing else to add to it. There's only one case right there. And 1 times 1 plus 1 over 2 equals 2 over 2 equals 1. And so all I'm going to do is put a little check mark right there. I have shown that the left side is equal to the right side in the smallest possible value of n that I could ever use, n being 1 right here. So we have verified a base case is true. The lowest possible integer value that we might want to use in this formula, n being equal to 1 is the smallest thing. And in fact, honestly, n equals 0 is going to be correct right here also. But adding up the first 0 integers doesn't really make sense to me, I guess. It doesn't. Again, that's a triviality right here. We're looking at the bigger picture here. So now for step 2, what we want to say is this. Assume that some case makes this statement true. And notice that we have already proven that there is at least one scenario in which it's true, when n is equal to 1. What I would like to do is show that given that the n case is true, it must be that the n plus 1 case is true. So what I want to show is that given that this worked out for n equals 1, it must therefore be guaranteed to work out that for n equals 2. Then I'll know that n equals 2 is true. So then I can go and reuse the inductive step to say, and now I know that n equals 2 is true. I would like to use that to show that n equals 3 is true. Now that I know that n equals 3 makes it a true statement, we can say, given that n equals 3 makes it a true statement, let's use that to prove that n equals 4 is a true statement. But all of those sentences that I just repeated with different numbers are all the same version of, if it's true for one case, prove that it must be then therefore also true for the immediately following case. So we are going to assume that the sum from I equals 1 to n of I is equal to n times n plus 1. And notice, over 2, this is literally what we want to actually show. We're assuming it's true, but we're using this to prove that the next case must be true. It's the stepping part. So this is literally like a proof version of y equals mx plus b. We gave an initial condition. We're giving our guarantee that we can increase by 1 and that we're still going to get a same relationship. Use this to show that the sum from I equals 1. Now, notice this is the really important part here. What we're doing is that this statement right here had a bunch of n's that were in it. I want to prove that this statement is true if we bumped up the value of n by 1. So notice now our upper bound here goes up to n plus 1. Over here, n, I'm bumping it up by 1, so this becomes n plus 1. This n plus 1 is getting 1 bigger, so it's now n plus 2. Right? I just took all of my n's and swapped them out for n plus 1 in the same formula right there. If I can prove that this statement being true forces this statement to be true, then we did it, right? And I'm going to just write that right here. Right? So if I can prove that knowing that any one case is true guarantees that the next case is true, given that we've already shown that one case is true, it must be true for all cases. I will then know that this formula is good for all positive integers n. So let's go ahead and do it here. So what the heck am I going to do in this case right here? So the point to me here is I get to know that this statement is going to be good right here up top. That means that this is maybe like a substitution that I can use. So I think that what I'm going to do right here is I'm going to say, listen, this summation right here looks like it's super duper closely related to this summation here, whereas this polynomial over here, I don't quite see how I'm going to transition from this polynomial to this polynomial right here, but I do see that these sums look super closely related. So I'm going to start with this quantity right here, and I'm going to say, look, notice that the sum from I equals 1 to n plus 1, what does this actually look like, right? So I get, let me say, I want to show that the sum from I equals 1 to n plus 1 of I is equal to n plus 1, n plus 2 over 2. All right, so what I'm going to do is I'm going to rip apart that sum on the left right here. Right here. I know that what this looks like is the sum of the first n plus 1 integers. So this should really look like 1 plus 2 plus 3 plus dot 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 plus n plus n plus 1, right? We're adding up the first n plus 1 integers. That's what we've got on the left. This I'm claiming is equal to n plus 1, n plus 2 over 2. All right, now what I'm noticing here is that the first n terms are actually something else that I recognize right here. This looks like this is really just the sum from I equals 1 to just n of those integers plus n plus 1. All right. So I've noticed that what I've done is I've taken one of the terms in the expression that I want to show, and I've found a way to rewrite it in terms of the expression that I'm allowed to assume is true. So we are assuming that this statement up here is true, so you should notice that means that it's acceptable for me to substitute this sum that goes up to n in exchange for this polynomial right here. I'm assuming that the n case is true. I'm trying to use that assumption to show that the n plus 1 case is also going to be true here. All right, so I'm going to go ahead and swap this thing out by n times n plus 1 over 2 plus n plus 1. And I think all I got to do here now is just maybe do a little bit of algebra. I think I want to get a common denominator here with these guys. So I multiply this guy by 2 on top and bottom so I can incorporate it into the common fraction here. It looks like I'm going to get n squared plus n plus 2n plus 2 over 2. And what is that really giving me here? This is n squared plus 3n plus 2 over 2. Well, I can factor this guy. It factors into n plus 1, n plus 2 over 2. Looks like we did it. So here, by assuming that the statement that we wanted to prove was true. So this is kind of the thing that people I think struggle with proof by induction, is that one of our key components here is the statement that we're trying to prove is true. One of our steps along the way is assume it's true. But we're not just assuming it's true and saying, oh, well then we're done. We're assuming it's true in the effort to show that it implies that the next case must also be true. And the reason why this helps us is because we've already proven it's true for the lowest possible case. So this case says it's true for case 1. Inductive case says that 1 implies 2, 2 implies 3, 3 implies 4, and infinitely on forever, right? Because now that we've shown that if the n equals 1 case is true, then the n equals 2 case must be true, then that gets us all possible cases that are out there. All values of n must therefore be able to work, because I've proved that from any one, the next is true. If any one is true, the next is true, and I got the lowest possible case to start from. So from that, we could build an infinitely repeating, like the math would be exactly the same. Since it's true for 1, it must be true for 2 by this math. Since it's true for 2, it must be true for 3 by basically the same math. Since it's true for 3, it must be true for 4 based on the same math right there. We're just replugging in the same numbers, right? So in every proof by induction, you're always going to do a super, super easy base case at the beginning. I've seen 1 or 2 proof by inductions where this wasn't even super obvious right here, but that's relatively rare. Usually verifying base cases, it says verify for a reason, because it's usually a really simple step. And in step 2, you are always going to assume true to be the thing that you want to prove. But then you've got to prove that that same expression, except where we've swapped out n for n plus 1, you need to prove that that's true. But you get to use this as sort of like a substitution, perhaps, along the way. It's often used as a substitution, not always, but you get to use this, and we did use this right here. And so I just want to say here, this part right here, by the assumption that the n case is true. That's what allowed us to make this substitution right here, is we assumed that the n case was true. But our goal stopped being to prove the n case, which was our original problem. Our goal became to prove the n plus 1 case based on the n case right there. So bumping up those n values to n plus 1, as I said, or perhaps start at n minus 1 and bump it up to n, or start at n plus 37 and prove it for n plus 38. All those would be acceptable inductive steps right there. All right. So we have proven then by induction that base case in the inductive step so we've proven by induction that the formula So what we've done is we've proven by induction that this formula is true. And very importantly, I feel like I kind of left this off here. Very importantly, we didn't prove It's true. We proved it's true for all positive integers greater than or equal to 1, greater than or equal to 1, because that was where my base case started. If my base case was n equals 7, then we would have proven that the statement is true for all n greater than or equal to 7. Sometimes with induction, it's one of those things where it's hard to prove it from the very, very, very base case, but maybe you can just do the math for the cases where n equals 1, 2, 3, and 4, and then you start your induction process at n equals 5. Like sometimes some stuff like that happens. So sometimes it's helpful to do more than one base case and start your induction step a little bit later, because maybe you've got some square root of x minus 3 in your terms right there, and you don't have any sensible way to plug in x equals 2. Then maybe you like start a little bit later in your process, but that's okay there. All right. So now what I want to do is, now that we've done our first proof by induction, we're going to do another proof by induction, or two more proofs by induction, but they're going to be to prove the convergence of a sequence right here. So something else that's new for us right here is that this sequence is defined recursively. What that means is it is defined based on previous terms in the sequence. So a recursively defined sequence always starts with a base case, and then it includes a recursive step. That means that the next term in the sequence is defined based on the previous or maybe multiple previous terms in the sequence. I'm hoping that immediately you guys are thinking of the Fibonacci sequence. You know that that's where to find the n plus 2 term, you add up the n plus 1 and the n term together, the previous two terms. So sometimes recursively defined sequences depend on more than just the previous one term. Maybe you need several previous terms in there. That's okay. This is recursively defined because the next term is dependent on knowing previous terms. That's how you calculate the sequence. So according to the monotonic sequence theorem, right? Is that what it's called? I always think of it as the monotonic bounded sequence. It is called the monotonic bounded theorem. Yeah. So, according to the monotonic bounded theorem, I just got my words wrong right here, bounded theorem, if we can prove that this sequence is both bounded and monotonic, then we'll have shown that it converges by the theorem. Note that the theorem doesn't talk to us at all about what it converges to, just that it does converge as opposed to diverging. In this case, then, our process is going to look like we need to prove it's bounded, we need to prove it's monotonic. Knowing those two things allows us to conclude by the theorem that it does converge. A nice thing to do afterwards, hopefully, and this is the thing we're going to say attempt, is we are going to attempt to determine what does it converge to. Once we know it converges, then maybe we can do a little bit of fancy math to figure out what must it converge to, as opposed to just making a guess. So our first thing to do, as we are stating our instructions, is to prove that this sequence is bounded. So we've got our definition of the sequence up at the top of the screen right here. Let's start by looking at the first few terms of this guy right here. So I just want to plug in some numbers right here and see what we're going to get. So the first one is easy. I can see that a sub 1 is equal to 2. I literally have been given that piece of information. Based on our recursively defined step right here, it should be that a sub 2 is going to be, so a sub 2, so that's like letting n be equal to 1. Then I'm going to get, this should be equal to 1/2 a sub 1 plus 6. That's going to be 1/2 times 2 plus 6. That's going to be 1/2 times 8. And that's going to be 4. So there's my second term in the sequence. It appears to be 4. I'm going to do the same steps and kind of compute a few more values here. And again, this is one of those things where, like, this is really not a computation-based unit out here, except that you should always be doing a little bit of this like exploration. And you should also notice that doing this by hand is a little bit tedious. This is a place where I would strongly encourage you to get involved with a little bit of technology to help yourself kind of do a little bit of the exploratory parts of these things out here, the intuition building parts. Pretty helpful. So the question is, where are we going with this thing? This is 5.5 now because we're looking at half of 11. If I keep going, a5 is half of a4 plus 6. That's going to be half of 5.5 plus 6. And that's going to be half of 11.5, which should be 5.75. And let's do one more here. And what do we see happening here? I guess I want to say it feels like this is converging to 6. That's what it feels like to me. And maybe you want to compute a few more terms to feel better about that. Fortunately for all of us, I don't care about your feelings. I care about what we can prove, right? So feelings are good. Sometimes they point us in the right direction, but there's about a billion cases where we can see that our intuition can lead us astray sometimes. And so, well, this is evidence gathering. I think it's pushing me in the right direction. I think I do want to prove that this thing converges rather than diverges, but it's not clear to me that it does. But after I've done a little bit of computation, I'm like, okay, I could see it. You could talk me into that without without any formal statements out there. So I'm saying it feels like this converges to 6. Or at least like it's bounded above by 6, I should say. Maybe it's actually converging to 5.9. 6 would be an upper bound. It wouldn't be the least upper bound, but I at least feel like I guess what I'm really looking at here is it seems like we keep on adding a number that's less than 6 to 6 and then taking half of it. So I feel like that's what's happening here. So let's attempt to show by induction that our sequence is bounded above by 6. So I want to prove by induction that this recursively defined sequence is bounded above by 6. So we're going to do our two-step process. 1, the base case. Well, base case is pretty easy. A1 is 2. 2 is less than 6. Done. Base case, trivially easy right there. We just wanted to show that for the first term in the sequence, our desired property held. The first term in the sequence was a sub 1 being equal to 2. The property we were interested in showing is that it was bounded above by 6. 6 is in fact a good upper bound for the number of 2. That's it right there. The base case is rarely exciting. In fact, sometimes I struggle with the base cases because I'm like, I don't even know what I'm supposed to be saying because it's so obvious. Now our inductive step. We're going to assume a sub n is less than or equal to 6. Use this to show a sub n plus 1 is guaranteed to also be less than or equal to 6, right? If I assume, and like literally, this is what we're trying to actually prove overall right here. A sub n is less than or equal to 6. That's literally saying the nth term is bounded above by 6. This is literally what we want to show. We're assuming it's true. But we're assuming it's true in the effort to show that the next case must be guaranteed to have that property based on the previous case having that property. That allows us to go from step 1 being true to knowing that it must be true for step 2, 2 for 3, 3 for 4, 4 for 5, off forever for all those n values that are out there. So I get to start from this a sub n is less than or equal to 6. And what I need to do is I want to build a statement Let's start with a sub n equals 6. Build a statement about a sub n plus 1. All right. And especially when I have inequalities, I like to sort of start from something at the core and construct some pieces around it right here. So what I know my relationship is right here, and I should just write this over here. Let me just write this thing out. A sub 1 equals 2. A sub n plus 1 equals 1/2 of a sub n plus 6, right? That was our sort of the problem that we're working on right here. So what I've got is I've got that a sub n is less than or equal to 6. We're assuming that that's true. If I want to build a statement about a sub n plus 1, I can see that a sub n plus 1 does involve an a sub n. So what I'm thinking is, let's go ahead and add 6 to this inequality. Let's go ahead and divide both sides of this inequality by 2, and then we'll have created a statement about a sub n plus 1. So I'm going to go ahead and do a sub n plus 6 is less than or equal to 6 plus 6, which is clearly 12. And then half of a sub n plus 6 is less than or equal to half of 12. And 1/2 of a sub n plus 6 is by definition what a sub n plus 1 is. Well, there we go. It looks like we did it. So by assuming the n case was true, we were able to show that the n plus 1 case was true. All right, so we did it. I mean, this just gets the check mark right here. Um, so we've proven by induction that sequence defined by a sub 1 equals 2, a sub n plus 1 equals 1/2, a sub n plus 6 is bounded above by 6. Now, let's do another proof right here. So we did one proof by induction to show one of the required two properties for the monotonic bounded theorem. Now let's prove the other part of the monotonic bounded theorem. We also need to show that this is strictly a monotonic function. It never changes direction. It never at some point like gets, and in our case here we've seen by our example that it is an increasing sequence right here. Every time we create a new number, it's always bigger than the previous from what we've seen so far. So that's certainly what I'm going to estimate is that it is increasing right here. And if I can show that it is always increasing, increasing means it's monotonic, and we've already proven that it's bounded, so that will tell us that it must converge, right? So let's do another proof by induction here. So I'm going to do our base case. Now notice that in this case, our base case is ever so slightly different than before. Why is that? Well, how do you prove that we are increasing if you only look at a sub 1? Can't just show this by only looking at a sub 1. So just notice, although this is referred to as the base case, I can't look at one number and say if a sequence is increasing or decreasing just by saying to you, oh, a sub 1 is 2. It's a change between two terms in the sequence. So the base case in this case here is going to be comparing the first and the second term. So I think all I got to say is a sub 1 equals 2, a sub 2 equals 4. Check mark. I don't think I have anything else to say here, right? And we've clearly increased from the first term to the second. Obviously increased from first term to second. Right, so we know that from the first term to the second term, this is an increasing sequence. Now, let's assume that we do get increase from the n to the n plus 1 and show that we get from increase from n plus 1 to n plus 2. Our inductive step. Assume a sub n plus 1 is strictly greater than a sub n. Use this to show. Remember, this is where we take our n terms and replace them all with n plus 1s. So n plus 1 becomes n plus 1 plus 1. And so we're going to use this to show that a sub n plus 2 must be greater than a sub n plus 1. We're showing that the relationship holds for two adjacent numbers implies that it must hold for the next two adjacent numbers. Right? So we are going to start with a sub n plus 1 is greater than a sub n. And what I'm going to do is incredibly similar algebra as I did with the previous example. It's not even going to be super exciting right here, is that I'm going to go ahead and let me just make my arrow go down right here. Is I'm going to go ahead and do very same algebra steps here. A sub n plus 1 plus 6 is greater than a sub n plus 6. That's got to be true. I should be able to take a half on both sides. Well, this is just the definition of what a sub n plus 2 is. This is just the definition of what a sub n plus 1 is. So we did it. We nailed it. We assumed the first relationship. We used that assumption to prove that the one step up relationship must therefore also hold. So again, we know that a sub n plus 1 is greater than a sub n was true for at least one case. We showed it for the base case. Now we see that the base case implies that it must be the case that a3 is bigger than a2, that a4 is bigger than a3, that a5 is bigger than a4, on forever out there. So that's why this has proven this true that this is increasing for all integers n. So we've proven by induction that a sub n, the sequence a sub n, is strictly increasing. So now we have proven by induction that it was bounded above. We've proven by induction that it's strictly increasing. Those are the two requirements for the bounded monotonic theorem, and therefore we can now officially conclude that this sequence for sure converges by the bounded monotonic theorem. However, we don't know what it converges to, right? So now maybe let me just make this kind of claim right here. This is my stupid way to write the bounded monotonic theorem. We showed both the two parts on the left. We got the part that's on the right. So, so now let's go ahead and wrap up our video here by saying, can we do some tricky thoughts here to kind of help ourselves figure out what it must converge to? And here's my idea with this one. If it's going to be the case that the sequence converges to some limit L, then it certainly should be the case that if you just bumped up every term in the sequence to its next slot, if you considered the a sub 1 to actually be a sub 2 and on forever, so that you're really just sort of one term ahead all the time, it still should converge to that same value of L. It's not like it's going to fall over the top of L or something like that. I mean, this was an infinite sequence that was converging to a number. Who cares if you're one step ahead? You're just converging one n, well, it's not like we converge by a specific n anyway. It still takes an infinite amount of n to get there. Since we're letting n get infinitely large, it doesn't matter if we let n be n plus 1 instead of n, because it's still letting n go off to infinity, right? As n goes to infinity, there's no distinction between n and n plus 1. Maybe that's the statement I should make here. Right? So basically this is me saying, who cares? We could swap out n for n plus 1. If one of these limit statements is true, then the other one must also be true because n's getting infinitely large. So we know that our sequence a sub n converges to some L. We proved it converges. We proved this above. Therefore, so does the sequence a sub n plus 1. This is literally just like rewriting the variable n as n plus 1. It's not even really like a meaningful change out there. So what I've got is I've got these two statements must both be true. I don't think that's too far of a leap right there. And again, I think this statement in parentheses may be our key here. Since we're letting n get infinitely large, there is no meaningful distinction between n and n plus 1 if we're converging to some value L out there. So what I'm going to do is I'm just going to do a little smidge of algebra here. I know what a sub n plus 1 is equal to. I'm going to then say this is limit as n goes to infinity of 1/2 of a sub n plus 6. That should be equal to L. What I further know is that this limit is unaffected by constant multiples and by addition or subtraction. So this says to me this should be 1/2 times the limit as n goes to infinity of a sub n plus 6. I guess I want like two sets of parentheses right there. Should be equal to L. And I know that the limit as n goes to infinity of a sub n is L. And so it seems like I now know that what we converge to is 6. And I feel like this seems like magic, just like some of the other things that we did today were magic right here. But I really like this idea of sort of like doing these like little off by one sums right there, saying if this thing converges, who cares what you call the term? If you call that term the 7th term and I call it the 5th term, I don't care, because if we both go infinitely far out, we're both going to converge on whatever that one convergent number is, L. Remember that by doing the work that we did above, we had no idea what L was. I mean, we guessed it to be 6 up there, but you should not be making guesses like that. This is a chapter about proof. We guessed that it was 6, and we did find that it was 6. That should make you feel good about your intuition, but it's so easy to get tricked by these things, so don't rely on that right there. And so if I know that the a sub n sequence is going to converge to the same thing as the a sub n plus 1 sequence, again, this is basically like you and I looking at the exact sequence, but you calling a number the 7th term and me calling it the 6th term. It doesn't matter, because if we go infinitely far out, we're both converging on the same number, L. And so I just made a substitution from one into the next right here, did a tiny bare smidge of algebra right there, and proved that what we therefore must be converging onto is 6. And so I really, really like that this kind of concludes with some kind of, man, this just seems like some sneaky backdoor algebra right there. But I hope that you can kind of feel your way to this statement being true right here. If a sequence converges to a number L written as a sub n, then just writing it as a sub n plus 1 doesn't really make any difference, because of the fact that the n's are getting infinitely large. And we can use this to our advantage algebraically right here. This is something that doesn't always work out so nicely or at all right here, but every once in a while this is a really practical idea for proving what we do converge to. What you're going to end up seeing in chapter 11 is that we're going to prove a whole mess of convergence without being able to prove at all, even getting remotely close to what the actual value is that we're converging to. We're going to do the best we can. In this example right here, we happen to be able to prove that it converges, not just that it converges, but to 6. I want to go so far as to say that's sort of rare. We shouldn't expect to be able to identify what we converge to in all cases. There are some really, really, really difficult convergence proofs that are out there that are going to be sort of beyond our capabilities, that identify what value things converge to. I'm going to kind of point you guys towards a couple of those like interesting articles and videos that are out there on the internet this chapter, but these are things where, like integration, the difficulty curve on this is pretty dang steep, where some of these things get to be outrageously difficult. When asking relatively simple questions, we're going to define some easy looking sequences, and it's going to turn out that it's going to be some like crowning achievement of one of the smartest people ever's lifetime, is that they proved what it converged to and being the first person to do so. And it's like there's some heavy ones that are out there. So this is kind of a special case in that we got it. So there we go. This is proof by induction. You have to be able to handle proof by induction. We are now writing proofs in a lot of this chapter rather than doing computation. And so as I harass you guys about on the homework all the time, it matters that you are communicating, because this isn't just like, see, I got 7, so 7's the answer. Proofs are a bit different than that. They are going to require you to write some sentences. It's true. They're going to require you to be well organized. They're going to require you to think on your own creatively about how you're going to do these steps. You should notice that it wasn't obvious at all what math I should be doing for any of these inductive steps that I did right here. Obviously, I knew what problems we were kind of coming up against. I'd obviously prepared this beforehand. I can tell you that proof writing is maybe one of the most like artistic components of math, even though it is the most like scientific part of math at the same time right there. It is the thing where it is irrefutable proof that some statement is true. that's hard to arrive at otherwise. But you guys will end up seeing a lot of this, that it requires some pretty crafty decision making on your part, how to use one piece of information to guarantee that another piece of information is true. So you'll experience that out here in this chapter. So that wraps it up for for section 11.1 here. And next week we're going to pick up with 11.2, which is series. A series is just the sum of a sequence. So an infinite sum, you should acknowledge that an integral is a series. It's an infinite sum. An integral is a special case of series. We would like to look at series a little bit more generally, as rather than just areas underneath curves, although we will use series to help us understand some integrals we can't do. We'll also use integrals to help us understand some series we can't do. They're very closely related, so we're going to use them kind of interchangeably, not interchangeably, but we're going to use them back and forth to help each other out a little bit in this chapter. So I will see you guys next week for section 11.2 on series. Have a good one.